Hi, good afternoon, everybody. So today we will continue our discussion on Newton's laws. In particular, we will start Newton's second law discussion. I just want to do a sort of an early semester check-in. Just make sure that we are staying on the right track. Here are some survey questions. I'm just gonna pull up the poll and then please go ahead and put your answer in there, okay? Just two choices, but my generic pool has more answers. So it's either A or B. Okay, few more seconds, some last minute vote. Any last minute vote? Okay, all right, I'm going to go ahead and end this. It looks like we're quite evenly split. All the components accounting to your grade, exactly 50-50. So pre-lecture checkpoint questions, flipped physics counts 10% of your grades, online homeworks 20%, and two midterms each will count for 20%, and final will be 30%. Okay, those are all the points that count into your grading. There are extra credit of the pre-assessment, which is already done, and there will be a post-assessment at the end of this semester. That's 1% extra credit. So that's all. Now make sure that you're trying to get all the points you can, and just take advantage of those, such as homeworks and pre-lectures. Those are lower stake than the exams. Okay, just wanted to quick check in, make sure that you're aware of all the components that could impact your grade. Yeah, pre-assessment is extra credit, does not, it's only gonna give you 1% extra point on your grades. Not gonna affect it in the negative way, only gonna affect it in the positive way. There will be a post-assessment, the same questions, just do it one more time. Okay, all right. Another question. While you're voting, I'm just going to answer the question someone asked. Will there be a study guide for the exam on the 9th? Yes, I will post a practice exam. It will be in the format of sort of a written exam, but it's not going to be, it's going to be a little bit different than the online exam in the sense the online exams does not have a sort of, the written part is all you enter your answer using your computer, so it's multiple choice kind of thing, so that's different. But in terms of the type of questions, it's going to be very similar. So I will post a practice exam and a practice solution for you online, okay? Okay, all right, seems like any last minute vote? Seems like I get majority of the votes coming in now. Let's take a look. I'm gonna close it. I'm so pleased that majority of you know how to find out information, or at least know about my office hours. It's on Blackboard, and I encourage you to come and ask any questions that you have, okay? And office hour link is different from the class link. So just go to course information. There is a link for office hours. So Wednesday 3 to 4 and Thursday from 11 to 12. Now, if you cannot make it to any of those times, you should email me and set up a separate meeting too if you have questions, okay? Third question. All right, just a few more seconds for last minute votes to come in. Okay, I'm going to go ahead and close it. Okay, so I want to say, I want to give this question because people often don't really realize how much time it can take. In the department, we recommend students that for every hour in class, spend 3 more hours outside of the class to practice and to study on that content. So 3 hours in class would be 9 hours out of the class. So even if you are spending 9 hours, that doesn't mean you are doing something wrong or you're not getting the material. It just simply mean you are actually spending a lot of, doing a lot of work to try to learn and try to get better. So that's all good. But in real life, I realize all of our students that our time are so we're so busy, right? You have a lot of other courses and sometimes you have to work. So mostly in the past, if I had survey questions, not everyone spent the 9 hours. It's really just a recommendation we put out to students to show them, yes, it is a hard subject. It is time consuming. People do spend a lot of time on this. Doesn't mean that you're not doing well enough. So if you find yourself struggling and spend a lot of time, that's totally common. So 3 to 6, that's the majority of your vote here. I would say that is a appropriate amount. So that's just give you an idea of what your classmates are doing. If you spend a little bit less or a little bit more, and don't worry too much about that, okay? Just try to see if you can do the problems and if you can understand the content. So just a quick reminder. Okay, so now let's continue to our discussion for Newton's second law. I realize our pre-lecture did talk about universal gravitation. So that is something we will actually have a separate chapter for it later. So don't worry about universal gravitation at this point. It will be discussed later. And Newton's second law, that is the one topic that we will have a lot of practice on, a lot of homework problem, exam problems, mostly just on the use of Newton's second law. And knowing how to draw free body diagram, knowing how to work out the forces is very important topic for this class. And later on, even when you solve other problems and using energy or momentum, or when you do rotational questions, you cannot get away with knowing how to do forces. So this is really fundamental thing that we need to master, okay? So we will start and begin our discussion today on Newton's second law. So if at the end you realize what the meaning of this particular little cartoon, I would say you understood what Newton's second law is saying. So previously, Newton's first law says a body will stay in motion if there's no net force applied. So if a net force is not required to keep a body moving at a constant velocity, what does a net force do? If something is moving already and there's no friction to slow it down, then this object will keep moving forever. If you apply a non-zero force on it, it's going to change the status of the motion. It's either going to make it speed up or slowing down, which means a force is required to change the velocity of the body, but not to maintain the velocity. Okay, so that is one thing that people often got wrong, saying to keep something continue to move, you need a force. But no, a force is only required if you want to change how the velocity is doing, change the velocity of a body. Now, the change of the velocity is acceleration. That's why force causes acceleration is what Newton's second law is trying to tell us. And we can also think about this qualitatively. So what does the acceleration depend? Does the acceleration depend on the amount of forces, or does it depend on the mass? So the acceleration, if you were think about to yourself, you were to throw something with a very large force and with a very small force, the same object, right? When you throw it with a larger force, you're giving it a bigger acceleration. That makes sense. But you can use the same amount of force, but one time you throw a can of soda, another time you try to throw a gallon of milk. Now, the can of soda will travel further because it has a smaller mass. So with the same amount of force, if you're applying this force on a smaller mass, you'll end up with a bigger acceleration. So you can see acceleration will depend on both the force and the mass. So it is experimental fact. People have done experiment to find out that Newton's second law is telling us that acceleration is force over mass. The bigger the force is, the bigger the acceleration. The bigger the mass is, the smaller the acceleration. Or we write it using F net equals m times acceleration. Now the net means it's all the forces together, because there could be multiple forces applied on the object. When you add all of them up, right, that is the net force on the object. And force is mass times acceleration. Acceleration is a vector. The vector direction is exactly the same as the direction of the net force. Okay, so I just want to pause 1 second because I got a question here from the chat. The exams will be on Blackboard, yes. And it will be active. It will be active for 24 hours, and then you can choose to have, I believe, I don't remember it's 2 hours or 3 hours, maybe it's 3 hours. I have to double check. You will have 2 or 3 hours of time to start the exam to do it. So whenever you want to start it, whenever you're ready, you will go ahead and start it. But you can do it within that 24 hours, within a day. There is no equation sheet because it is open book. You can always refer to your notes for the equations. You are welcome to write up sort of a summary of equation for yourself to reference to for your exam. The solutions will include the detailed steps of the problem, yes. How many questions? The exam is multiple choice. How many questions? I don't remember exactly. I will let you know later, okay? There's definitely enough time for the exam. When is it due? It is due, again, it's March 9th, so it's due for that entire day. You can choose any 2 hour or 3 hour period to do the exam. We have to do it within that day. And on that day, we will not have class time. So that day is just exam day, okay? All right, hopefully I answered all the questions. Let's continue with our discussion. If you have any more questions about exam, you can always ask me later. So when you have all the forces acting on the object, in this case, look at there are 4 forces, right? When you add all of them up, the top and the bottom cancels, right? This one and this one, they cancel. And the one to the right is much bigger than the one to the left. So overall, when you add them up, you can see that the net force is actually pointing to the right. So giving you an acceleration pointing to the right-hand side. Okay, so this is what Newton's second law is telling us. The checkpoint question is a direct application of Newton's second law. The net force on the box is in the positive x direction. Okay, so there's a net force in that direction. Which of the following statements best describe the motion of the object? Well, its velocity is parallel to the x. Well, we don't know that, right? you can be moving to the left, and then you all of a sudden you apply a net force. B, its acceleration is parallel to the x. Well, that is correct because F net equals ma. So if the net force is to the right, which means the acceleration is to the right. Now, we cannot say anything about the velocity. We don't really know the status of the motion. We only know that the acceleration at the moment is the same direction as your net force. So that is B, okay? There's also a question from pre-lecture that I would like to talk about. There is a force. So, okay, at the t equals 0, at that moment, we don't really know in what direction the mass is moving, question mark, but we're applying a force to the right. 1 second later, the mass is moving perpendicular upward. So think about it. Which of the vectors could best represent the velocity at t equals 0? So because the force is applied to the right, meaning that my acceleration must be to the right, right? And we also know the acceleration is the same as in change in velocity. So if your velocity final is v1 and the change of a velocity is delta v, which is to the right, the same as a, in what direction is your v initial? So v, we know that the change delta v is equal to v at a later moment minus v at an earlier moment. So we know that v naught plus delta v is equal to v1. So you can see that the v naught has to be this vector. So that delta v and v naught head to tail add up to be v1, right? So you have to be diagonally to the left. You can, that's one way to think about this. There's another way to think about this is you can think of, okay, so originally my velocity is moving to the left, upper left corner. You can think of this having a component to the left and also moving upward. So you're sort of moving to the left and up at the same time, right? And the force hits you, there's a force, so the acceleration applied sort of made this component go away and leaving only the perpendicular component. So that's another way to think about this, which will also give you answer D. Okay, so this is a clicker question. I want you to vote on this. Again, right now we are simply doing a direct application of Newton's second law. Okay, so so there's a question on why it's not B for the pre-lecture. So imagine if it were B, okay? So you were moving, the velocity was moving this way, and you apply a force this way. So you can see there's no way for the object to move perpendicularly later. You must be moving even further to the, you must be moving further to the right and upward. There's no way you could be perpendicular, right? That's why it's not B. If you're already moving to the right and you apply a force pushing you to the right even more, there's no way you could be going directly upward. That's why it's not B. Thank you for asking the clarification. So let's look at this clicker question, okay? I'll let you, I don't think we need to go to breakout room, so I'm just gonna let you vote. Okay, let's go for another 15 seconds for the vote. Any last minute vote? Okay, I'm going to go ahead and close this. Here are the results, the distribution between A, B, and C. So B and C are roughly the same. A gets most of the vote, but still not a majority. Let's take a look. So to compare the net force between these two objects, I think B is indeed a distractor, a confusing one, because you may look at it's the F that's pushing both of them, right? So if you think, okay, I have the force pushing on both M and 2M at the same time, maybe it's the same force. But you have to realize that is not the net force that's acting on these two blocks, right? The M, for example, has this F pushing to the left, but you know the 5M actually is pushing back on the little 1M to the left. Now, at the same time, the 1M is pushing on 5M. So this little F, so this 5M will experience a force to the right, but it's not equal to the big F. So it gets quite complicated. To be able to solve this, you need Newton's third law, but we don't need to solve what F is, what A is. All we are caring about right now is the net force on the block and the net force on the mass Fm. So no matter how many forces acting on it, the F net is always M times A. Okay, so if I'm looking at 1M is F net equals 1M MA. If I'm looking at the 5M, is F net for 1M for 5M is the 5M times A for the 5M. But there is one condition that if you're pushing both of them together, do you think these two blocks have the same acceleration? Do you think that the 1M acceleration is equal to A of the 5M? Why not? If someone said no, then why not? What happens if they don't have the same acceleration? Would they be able to move together? One will accelerate more, then they'll have to come apart, right? So because if you're pushing both of them, they're moving together, implicit, it implies that they have the same acceleration. I know it's not explicit given, but it has to be true. Okay, if one accelerate differently than the other, they're gonna fall apart. They won't be close to each other, not gonna have contact. So they have to have the same acceleration. So indeed, I need only one A to describe it, okay? So we can see that in order for the 5M and the 1M to have the same acceleration, the force required to accelerate the 5M needs to be 5 times the force of the little 1M. So the 5M is bigger, okay, than the 1M. That's the net force. And regardless how many forces acting on them, but the total one must be bigger than the other. Okay, so A is correct. Okay, so again, we're doing, here is another question for a direct application of Newton's second law. Has to do with circular motion. You're driving a car with a constant speed around a horizontal circular track. So this is a circular motion with constant speed. What is the net force on the car? So we know that for a circular motion with constant speed, in what direction is the acceleration pointing at? So in what direction is the acceleration? We gave a name to this acceleration. For circular motion, acceleration is pointing which way?
Towards the center.
Inward.
Inward, toward the center. Yes, very good. You're right. Acceleration always point toward the center. This is the centripetal acceleration. Yes, so there is a non-zero acceleration, which means there must be a non-zero net force. There must be a net force to provide the centripetal acceleration. So the force must be pointing radially inward toward the center of the circular track, just like the centripetal acceleration. Okay. Now in real life, this force, okay, what kind of force is providing this? It has to do with how the tire is pushing on the ground. You maybe have partial of the normal force on the ground. They have some static friction together providing this centripetal force and give you the centripetal acceleration that's pointing toward the center. Again, you can see we're just applying this over and over again, saying this direction and this direction is exactly the same. Okay, now I want to talk a little bit more about how we express gravitational force, because later on when we solve problems, we need to know what the gravity is. So go back to talk about gravity. We all feel the force of gravity on Earth. In free fall, if the gravity is the only force applying on the object, then you will have a gravitational acceleration going downward, which is 9.8 meters per second squared. You put a negative sign if you want upward is the positive direction. So from Newton's second law, we know that this net force, which is the gravitational force, if the gravitation is the only force, then that's the net force, is equal to ma. Now ma becomes mg. The magnitude is mg. So force of gravity is F equals mg. That's where it comes from, right? It means when gravity is by itself, it will accelerate you in free fall with an acceleration of g. So a lot of times you see your weight is also mg. So if you tell people I have a mass of 50 kilos, for example, then you will say 50 kilos times 9.8 meters per second squared, and you get roughly like 500 newtons, and that's your weight. And you can change that to how much pounds, that's the weight, the same thing. Weight and gravity is the same thing. The newtons in SI units, the standard units is kilograms times meter time divided by a second squared. Mass is an intrinsic property of an object, independent of where it's measured. It's not the same as your weight, because you can weigh yourself here on Earth, and you can weigh yourself on the moon, right? You will not get the same reading, but you have not changed your mass. You're still the same person. You still have the same amount of mass in your body, right? So if you only look at the weight, you can realize, oh, I have lost weight by going to the moon, but really you haven't really lost the weight. You still have the same amount of mass. So that's why we say mass is an intrinsic property, independent of where you measure it. But the force of gravity, your weight, actually depends on in which gravitational field you are in. It's possible that if you are weighing yourself in the falling elevator, you actually won't get a reading, but doesn't mean that you don't have any mass, right? It's really just depending on your acceleration at the moment, also the gravitational field that you're in. So if you wanted to translate 1 kilograms of mass is so it'd be 1 kilo times 9.8 meters per second square, give you 9.8 newtons, and that's roughly 2 pounds of weight. Okay, so that's how these different units translate. So let's look at this quicker question. Here we are getting toward actually using Newton's second law to solve some quantitative problems. This is maybe something very familiar to you because it's similar to an elevator checkpoint we have seen previously. You have an object of mass m, it's being pulled up by a cord, and you have an increasing speed. You're pulling it upward. How does the tension in the cord compare with the gravity of the object? Okay, I will let you discuss this question for about a couple minutes. You can take a screenshot before you go to your breakout rooms. Nobody is active in your breakout rooms. Make sure that you let me know and I can switch you. Okay, 10 more seconds for everybody to finish voting. Okay, I'm going to go ahead and end the poll. All right. Seems like majority of you guys are in agreement for the choice A, that tension is bigger than the gravitational force. To answer that question, the first question we need to answer is, in what direction is your acceleration of the mass m? So what do you guys think? In what direction is the acceleration?
Upward direction.
Upward direction, you said? Yes, yes, very good. Upward. So how do we know it's upward? It's being pulled up. Does that mean it's upward if it's being pulled up? Pulled up means what? Means velocity is up. It's going upward. Velocity is an upward direction. And what else do we know about the velocity? Is the velocity getting bigger or smaller? It increases, yeah, increasing speed. So not only you're moving up, you're also speeding up. The speeding up part tells us acceleration is upward, okay? So that acceleration of the mass is upward. If I gave you the same question, but instead I said an object is being pulled up on the cord at a speed that is decreasing. If I say the speed is decreasing, then you will tell me the acceleration is in what direction?
Downward.
Downward. If I'm saying it's going upward, but decreasing speed, then your acceleration is actually downward. Be very careful of what information the question is giving you, okay? So speeding up, acceleration is upward. Okay, which means I have two forces here. One is the tension, one is the force of gravity. They cannot cancel out, right? One has to be bigger than the other, so tension must be bigger than gravitational force, giving you a net force that is going upward, so giving you that upward velocity acceleration. So A is correct. Very good. Now this one we will get to practice solving problems. Here it's the same problem, right? But now instead of just saying it's increasing, I even tell you at what rate it's increasing. And the solving for the tension T. Solve this problem together. In the, so okay, in kinematics, we talked about the approach of solving problems. First, draw a picture. Again, here you have a picture, right? Next, in your kinematics, we will say label the quantities. You do want to label the quantities, but most importantly, here you need to draw the free body diagram where you can label the forces. Free body diagram, you label the forces, and then you think about what physics is involved. And then you solve for the question you wanted to solve. So question, picture is given, now label, let's label the quantities. Okay, okay, so we know we are curious to draw the free body diagram. Okay, so here are some sub-steps of how to draw the free body diagram. First, you isolate the object of interest. When I say isolate, meaning that you put your attention on this object. Isolate the object of interest. In this case, we're interested in the mass m, right? So that's the object we want to think about. And then think about what other forces, what other objects would you in contact with.
Professor, we can hear you.
Cannot hear me? Or maybe I just need to get really close. Can you hear me now?
No, we still can't.
Hello, can you hear me now?
Yeah, it's better.
Yes, so it may just because of my mic. Thank you for reminding me, okay? So second step, think about what other object this one interacts with, and then draw all the forces. So let's do that. Let's draw the forces. I need you. This object M is interacting with the cord. So you have a force of tension going up. This object is also interacting with the Earth. Earth is exerting force of gravity on the object. So I have these two forces. Okay, so I draw and label the forces. What other quantity is given? It's giving me about its mass. Okay, so mass is given. Let me put it down. It's also giving me acceleration. So that's all the quantities. Do I know what acceleration is? Do I know, is this number given?
It's 5 meters per second.
Yeah, so acceleration is a change of velocity over time. So it changes 5 meters per second every 10 seconds. So change over time. It's 0.5 meters per second squared. That's your acceleration. That's also given, okay? I've labeled these quantities. All of these is given. So now let's think about the physics. I've done this, we have done this. What kind of physics is applicable here? We cannot really use kinematics, right? It's not really asking about the position or velocity. It's asking about the force. So what physics law we need to use? That is the topic of today. What is the physics law? Newton's second law. Thank you for those who shared. It's Newton's second law. And the question is solving for tension. Okay, so let's use Newton's second law on the object. Newton's second law says F net equals ma. All right, so always start from the basic fundamental equations. So, okay, when we apply it on the object, apply it on this object M, what are all F net, all the forces? You have two forces, right? So how do we put them together? How do we write them? Do we write T plus Fg? Or do we write T minus Fg? How do we write this? Or Fg minus T? How do you represent the F net? It's a vectors. So we have to define a positive direction. So let's say I want positive to be upward, okay? T minus Fg, yes. So if I want positive to be upward, my T is in the upward, in the positive direction. So T becomes positive, Mg will be negative. That's why you have a minus sign. Okay, so net force have two forces. One is T, one is Fg. They put together like this. This is the left-hand side. The right-hand side, the mass is the mass. Acceleration is also upward. So that's acceleration also, you simply say A. Okay, and let's further elaborate this. T minus Fg is mg, right? Force of gravity, we just talked about this. Equals ma. So I solved T is what? Ma plus mg is ma plus g. So you can see I solve this. I recommend solving this algebraically and don't plug in numbers until you get to the very end. So here I can plug in numbers. 0.5 kilos. Acceleration is 0.5 meters per second squared. G is 9.8 meters per second squared. And you can just put everything together. All right. Okay, so you have solved for tension. It will be in the units of newtons. So that's your final units. Okay, so that's one example. Let's look at another example. Okay, so this one I will talk through this. I slide a book and the book's weight is given is in pounds across the table at a constant velocity. The coefficient of kinetic friction between the book and the table is 0.2. So the coefficient of kinetic friction, describe what kind of surface you're talking about. Is it smooth or is it rough? So it's just a property of the kind of surface you're dealing with. And we will talk about how to use that number later. First question is, what is the magnitude of the normal force acting on the book? And the second question, what is the magnitude of the force your hand is applying? Or again, solving for forces. So again, the first step is to draw a picture and label the quantities. So you need to draw the free body diagram. So again, in drawing the free body diagram, the 3 steps is 1, isolate the object of interest. In this case, the object that is moving is the book. You're interested about the book, right? Because all the forces is acting on the book. So we want to draw the free body diagram on the book. How many forces are there on the book? So we know, okay, then we have to think about in what object the book is in contact with. Well, the book is in contact with the surface, so you must have a normal force from the surface upward. The book is in contact with the earth, well, not directly touching, but it's under influence of the gravitational field, so you have the gravity. You're pushing the book, so you give it F of the hand. And there's friction, so friction is against the motion, so you have a friction little f here. These are all the 4 forces acting on the book. 4 forces. Thank you for those who put in. And someone even answered the question for the normal force, but we'll get there later. Up, down, and left to the right. You're right, 4 forces. Okay, so that's straightforward, right? Now let's solve the problem. Again, we use Newton's second law, that is a physics here, right? Newton's second law is a physics, and you will start with F net equals ma and applying it in each of the directions. So let's do this. We realize that we probably need to define a positive and negative direction, just like the previous problem. So we're gonna say upward is positive and to the right is positive. Okay, positive y, positive x. And the F net equals ma, starting from Newton's second law, again, your physics is Newton's second law, to always start from this equation, okay? But it is vectors. So you need to look at the x direction, y direction separately. You need to list Newton's second law on the x and y separately. So let's look at the x direction, the horizontal direction. There are 2 forces. One is your hand, right? One is friction. So I do hand minus friction because I define to the right is positive, equals acceleration in the x direction. So be very careful, you're looking at the force only in the x direction, so acceleration in the x. I claim the acceleration in the x direction is 0. How do I know that? How do I know the acceleration in the x direction is 0?
The velocity is constant.
Yeah, velocity is constant, very good. So that acceleration is 0 here. Now I do the same thing for y. There are 2 forces, one is up, normal, one is down, gravity. And the direction acceleration in the y is also 0. Simply, there is no motion in the y. It's not in free fall. It's not going up or down, right? It's not speeding up or speeding down, so 0. So you can see that, oh, it actually using Newton's second law, or maybe you have already figured this out by just eyeballing it. Normal force cancels gravity, the force from the hand cancels friction, giving it 0 acceleration in both directions. So your normal force has to equal to the weight in terms of its magnitude, which is 2.5 pounds. You can just leave it as that because it's forces. So pounds is okay unit. It's a totally viable unit for forces. You don't have to convert it to newtons. You need to convert it only if you there are other units that's meters per second squared. You need to be consistent. But here, you just say normal force is just as your weight is 2.5 pounds. And your force of the hand is the same as your friction. So to use the friction, we're gonna put a little mental note here. We'll get back to this later. You need to use the kinetic friction coefficient. I will get back to that. So the bigger this coefficient is, the bigger the little friction is. So it turned out friction is mu times normal force, but that's something we will come back to, okay? So at this point, we just wanted to show how to set up Newton's second law, how to solve the forces. We have solved for the normal force and we can solve for the hand once we do a little more practice on this later. Okay, here is a checkpoint question. It's a little variation of the elevator problem we did earlier. We have a box of the mass hung by a spring from the ceiling of the elevator. The elevator is now, when it was at rest, the L is 1 meters, extends 1 meters. So when box is at rest, so there are two forces. One is force of gravity, which is mg. One is the force from the spring, right? And we know the spring extends 1 meters when it's at rest. Now, if the elevator accelerates upward, then will the spring get longer or shorter or remains 1 meters? And we have done this already, right? So we know that if the acceleration is going upward, if this is at rest, then the spring force must cancel out gravity, right? So with that 1 meter extension, it cancel out the weight, which is mg, because it's at rest, so 0 acceleration. But when you are accelerating upward, when you have an acceleration upward, mg is still mg, your weight hasn't changed. But the spring force is different. So my question is, do you think the spring force right now, is it bigger or equal, or is it smaller than mg? The force that's pulling up, is it now the same as mg, or bigger than weight, or smaller than weight mg? What do you think? Greater, yes, it's exactly like the tension problem. With a acceleration upward, you need the upward force to be bigger. So this force needs to be bigger than mg. When it was mg, it extends 1 meter. When it's bigger than mg, do you think it extends more or less? It will be bigger, yes. So it will extend more than mg right now. So it has to be longer than 1 meters, because for a spring, the longer you stretch it, the bigger the force it provides. So from that, we know L must be 1 meter right now. And it has to be bigger than 1 meters in order for you to have an upward acceleration. So recall the spring force can push or pull, but the longer you stretch it, the bigger of the force it's gonna be, okay? Okay, now let's go to another very classical kind of problems, is measuring your weight on the elevator. Now when I said measured weight. The measured weight can change, but your weight will always be the same weight as long as you're on the same place on Earth. Okay, but this is a measured weight, is whatever your scale, the reading from the scale you get, can change depending on your status of emotion. The person is standing on the bathroom scale inside an elevator. When the elevator starts accelerating upward, what will happen to the measured weight? Now, if you're standing still and the elevator is at rest, you're measuring just your weight. Okay, 150 pounds, you read 150 pounds. But once it's accelerating, does this measured weight change? If it's changing, how? One thing I want to tell you is this hint is your measured weight is equal to the amount of normal force acting on the person. Okay, so to know what the measured weight is another question is asking about the normal force. I will let you discuss in your breakout rooms for a couple minutes. Okay, 10 more seconds for the voting to come in. Okay, so I'm gonna go ahead and close this and we'll take a look at this question together. And I see that, yes, measure weight will increase the majority of the vote, and that is correct. Very good. So if I didn't have you giving you the hint, so to be able to talk thoroughly why the measured weight equals the amount of normal force, we will have to wait until we do Newton's third law. But at this point, let's just say what you're measuring is amount of normal force that the person is receiving. Okay, and the normal force will increase, or the measured weight will increase as opposed to the reading it was before the acceleration. And yes, that is correct. Again, here we draw free body diagram. So what is the object of interest? So we should draw a free body diagram on what? On the scale or on the elevator or on the person? What is the object that we're interested in right now?
On the person?
The person.
Yes, it's on the person because it's normal force acting on the person. Very good. So on the person, normal force upward. Then on the person, you have weight mg coming down, or F of g equal to mg. And for the person, again, person is together in the elevator. So acceleration is the same acceleration for the person, for the elevator, for the scale, everything the same. Okay, so the person has the same acceleration upward, which means your normal force must be bigger than your force of gravity, which is mg, right? So if it were 120 pounds before, now you must be measuring a number that's bigger than 120 pounds. So your measured weight will actually increase. If you are falling in the elevator, then your measured weight will decrease. You probably have that feeling, right? If you're on a roller coaster and coming down with a really big acceleration downward, you feel like you're kind of not even touching your seat. In the case, the normal force is really decreasing or sometimes non-existent if you're free fall. Okay? In this case, it is increasing. A is correct. So now let's simply change this into a longer problem. Is now let's calculate the reading. So what is your reading right now? If you were 110 pounds, which was a 50 kilogram of the mass, what is the reading now if you are accelerating? So let's solve this problem together. First question, the first step is to draw a picture. I have already drawn a picture and label the quantities, which means you need to draw your free body diagram as well and label the forces. We've done that already. F of G and normal. Okay. And third step, think about the physics. Again, we're doing Newton's second law. Okay. So let's, and then we need to solve for normal force. Okay, that is the question. Okay, let's apply Newton's second law on the person. I'm going to define upward to be positive directions here. Okay, Newton's second law, F net equals ma. In applying it in y direction, so you have the positive normal force going up. You have gravity pointing down equals ma. Acceleration is also up. Okay, so this becomes mg because ma, so your normal force is ma plus mg. Okay, and that is m a plus g. Well, actually, in this case, I'm gonna keep them separate because I already know mg is your weight is 110 pounds. That's already given. So I'm just gonna say 110 pounds. And m is 50. A is 0.5. And that should give you 25 newtons plus 110 pounds. Now you have a choice of keeping it in pounds or newtons, but if in terms of bathroom scale, you probably end up using the scale of pounds, right? We don't really have a newtons on there. So I'm gonna convert newtons to pounds. It's 25 times 0.225 pounds plus 110 pounds, which is 115.63 pounds. Okay, so that is your new reading. It is different, it's more than the reading you had when you were at rest. Okay, so that's how you see we applied Newton's second law and we solved for the normal force. So you can see that is your reading on the scale. Okay, for the time we have left, I want to talk about normal force and how to calculate normal force when it's on the ramp, on the incline. We know how to do normal force on a flat surface. That's simple, right? You have mg, if it's sitting still, your normal force must equal to mg. We are very familiar with that. But if you are on incline, what is the normal force? So let's say you have a frog sitting here at the ramp with 0 acceleration. What is the magnitude of the normal force acting on the frog? This involves a common trick that we do is decomposing your weight into 2 directions. Okay, and that is something that people tend to often have difficulty with. So you can see that we always set up our coordinates, x and y, in the horizontal direction. We always say this is x, this is y. But for incline ramp problems, we actually rotate our axes to be along the ramp and perpendicular to the ramp. We actually rotate our x and y. Why do we do this? Because that is easier to solve problems. You can see that if we rotate our xy this way, because if we have any motion, it's always along the ramp, it's always up or down in the x direction. There's never really any motion in the y. You never really go into your ramp or leaving your ramp. It's always along it. That's why we set up our x and y this way. We rotate our axes. So if we rotate it, x and y, your weight, which is directly downward, this angle, can be breaking down into an x component and a y component, right? So these two are not new forces. This is just a component of your gravity. Okay, so a lot of times when we break it down, we cross out the original weight to show that we are not making up new forces. Okay, so the x component of that, you can see that this is angle theta. That's how, what's the angle of your ramp usually will be given in the problem, which means this is angle theta. How do we know this? Because let's say if theta is 30 degrees, in this triangle is 90, this must be 60 degrees. And this is also perpendicular 90 degrees. So this angle must be 30 degrees, the same as the angle of your ramp. Okay. So because of that relationship, in the triangle, sine of theta is the perpendicular, is the opposite side, which is wx. Weight, x component of x over weight. So your x component is weight times sine theta, which is mg times sine theta. Your cosine theta is the y component of your weight, this side, over weight. So your y component of the weight is mg of cosine theta. Okay, so that's something we will use over and over again in a ramp problem. So you can see that this is breaking down into 2 components. One is mg sine theta this way. One is mg cosine theta this way. Okay, So you can see that normal force and the mg cosine theta is both in the y direction. So here, if I apply Newton's second law in y direction, I have normal force minus mg cosine theta is 0. So normal force on a ramp is mg cosine theta. The answer to this question is mg cosine theta, okay? So that's how we do a ramp problem. Now, if you have extra forces in the x direction, for example, you have static friction, you'll add it in, or if you have kinetic friction, you'll add it in the x, but there will be more problems on that later. So for the ramp problem, are there any questions? Okay. So if there were no other forces in the x direction, you can see that if there were no friction, the frog will be sliding down, okay? Because in the x direction, if you apply Newton's second law in the x direction, F net equals ma in x. F net is only mg sine theta, nothing else, and equals ma in x direction. So you can see that the acceleration is going to be g sine theta coming down, right? So if you have an object here with no friction, it's going to slide down with an acceleration of g sine theta. Okay, if there's more friction, then we will work it out later. Okay, so that's all we have for today. Next week, we will continue to solve more Newton's second law problems. And we will add more information on how to work out the specific format for friction. Okay, so, okay. All right, so if you want me, someone wants me to go back slide with a reading on the scale, the one with the units is this slide, right? Okay, so that's all for today. I will see you guys next week.
Have a good weekend.
Thank you.
Everybody.
Thank you, Professor.
Professor,
Yes.
regarding my problem, I emailed, you know how you told me to email the flip physics, you know the link you sent me for the flip physics, and then you told me to email them?
Yeah, I said they say there's a link for email, but I think calling would be better. Did you try calling them?
Oh, okay. Well, I sent an email yesterday as soon as you sent me the link, and then
Okay.
someone responded to me. They said they're gonna work on it,
Okay,
and
okay.
they're gonna let me know. I'm still waiting on them to email me back.
Okay.
But if I don't receive anything for like the next hour or two, I'm gonna email them. I'm gonna email her again and ask her like for the updates.
Okay. Okay.
But my concern is the homework. I really don't want to miss it. I don't want to miss out on the homework and stuff like that.
You
So
won't if you you have two options. You can continue to wait. Well, I will just give you extension on your homework. I can give you 2 more weeks. That's no problem. But if you don't want to wait, or maybe wait, just wait and ask again today at the end of today. If tomorrow no answer, you could,
should I just create
like
another
you said,
account?
register for another account. Just do your homework temporarily over there, and I'll transfer it over here. I think that might be a better solution. What do you think?
Yeah, I think actually I was thinking about that too. So I'm gonna just wait till end of today, see what's going on. And if
Yeah,
by tomorrow they didn't get my account up and going, then I'll just create another account with my personal email.
yeah, and you might call them again just to see if you reach the same person on the phone call.
Okay, yeah.
They should be able to give you a quick fix.
All right, okay, yeah, that sounds great. I'll
Yeah.
call them too.
Okay, keep me posted, okay?
All right, for sure. Thank you very much. I really
No
appreciate it.
worries, no worries. And then I will for sure give you extension on this homework as well.
Okay, thank you.
Okay, bye.
Have a nice weekend.
You
Bye.
too.